So Giordano Bruno is a monk, humanist scholar. He's born in the Kingdom of Naples, and he is interested in the heavens, as are many of his contemporaries. Uh, he gets himself into hot water by publishing a piece in 1584 called The Ash Wednesday Supper on cause, principle, and unity, and on the infinite universe and its worlds. And he believed, quite contrary to many of his contemporaries, that the suns were actually distant stars. He was very, very in our sense, a very modern thinker. Um, that these distant stars had their own sort of exoplanets. He also held that the universe was infinite, um, and that the Earth could not possibly be at the center of the universe. And just this idea in and of itself that the universe is infinite is incredibly terrifying to the church, as it would be for many people, for common people who are used to thinking that you have the Earth at the center, then you have a series of spheres, planets, you have ether, and then beyond that you have God and the angels and the cherubim and seraphim and Jesus and everything else. And so it really it makes for a nice, neat, kind of cozy world. Um, but Bruno and other people are beginning to realize that this can't possibly be true for a number of reasons. So Bruno, unfortunately, is burned at the stake as a heretic, and this sends a powerful message: do not contradict the church. But the irony here is that many of these practitioners of the new science hardly meant to refute the existence of God. They would not have understood what you meant by a secular age. They were not atheists. They were most times actually deeply, deeply religious men. And in fact, they were often trying to demonstrate the beauty of creation in another, what they considered to be more precise way. It's the same thing as we'll learn about next week with Newton trying to get to the heart of creation through alchemy, for example. And just as astronomers and other scholars were looking outwards towards the heavens to understand the beauty of God's existence, others were looking inwards towards their physical surroundings, but also quite literally inwards to the human body. For example, on Vesalius, there's a great deal of interest in the functioning of the human body in this period, from the way that the muscles work to the meaning of the blood in human bodies. And there was difficulty getting to the heart, not to pun, but the heart of the matter, because dissection was really difficult. Given that the church's official opinion was that the human body, being created in the image of God, could not be corrupted through the process of dissection. And as such, the only cadavers that were available for this work, even for instructional use, were those of criminals who were condemned by, both human society and also, in a sense, God. So these cadavers were in high demand, and over the course of the late Renaissance and early modern period, the discipline of medicine becomes an ever more popular pursuit. And in order to be trained in medicine, you have to observe anatomical experiments and dissections. Universities and academies, especially well-regarded schools, such as those found in Pisa and Padua and Bologna, offered extremely well-attended dissections. As you can see here on the title page from Vesalius's De Humani Corporis Fabrica, which was published in 1543, so on the fabric of the human body. And this is considered to be really the first great modern work of science, of scientific anatomy, and really a foundational work of modern biology. You can also see the second images of the human body laid open with all the musculature visible, which depicted in a way that it was so precise and really far more realistic than previous anatomical drawings had been. Meanwhile, you have others, such as, almost a century later, people who are capitalizing on the new theories of Vesalius and others, um, that are circulating about the functioning of the human body. And again, almost a century later, William Harvey publishes um, De Motu Cordis, otherwise known as On the Motion of the Heart and Blood, in 1628. So Harvey, who coincidentally was trained at the University of Padua, Italy, published this 72-page book, which contained a fully realized account of the circulation of the blood. Now others had certainly come before him who had also postulated that the blood circulated through, they knew that it circulated through the body, through the arteries, but when it came to the heart and the ventricles, they had really an unclear idea of how that process took place. He was the one to figure out that it's the opening and closing of the heart. The heart is a kind of a pump. Interestingly, this work also demonstrates how widely accepted the heliocentric universe had become among natural philosophers by this point. His demonstration that the pumping ventricles of the heart at the center of the body was at the center of a circulatory system in which the blood moves in cycles through the body was compared to the new system of the universe, the heart being the sun of the human body. So he wrote that the heart of animals is the foundation of their life, the sovereign of everything within them, the sun of their microcosm. At almost the same time, Francis Bacon publishes his Novum Organum, New Method, which is one of the perhaps most groundbreaking works in all of the 17th century literature on the new sciences. Bacon attempts to create organization and cooperation within the scientific community by demonstrating how different fields of science relate to one another. It's really meant to be a replacement for Aristotle's organon. He postulates what would later become known as the Baconian method. So Bacon's method is an example of inductive reasoning. By reasoning using induction, what essentially Bacon means is that he's trying to find a finding or scientific findings through various steps based on accumulating data, or by building a case from the ground up. As I mentioned previously, this method starts with evidence gathering to prove or disprove an idea, rather than beginning with an accepted axiom. This lays the basis for what we now recognize as the scientific method, which was first laid out, at least again in the form that we now recognize it, by Robert Boyle. And again, we'll hear more about him next week. At approximately the same time, Johannes Kepler formulates his laws of planetary motion, which describe the form and operation of planetary orbits, and really put the last nail in the coffin of the Aristotelian system. His view of the orbits as ellipses rather than as perfect circles would later help Newton figure out how gravity works, because Kepler was able to figure out that the faster a planet moves more quickly, the closer it is, or covers distance more quickly, the closer it is to the star, which later would be key for helping Newton figure out his system law of gravity. So a rough contemporary of Kepler, of course, is Galileo Galilei, who's also an astronomer and mathematician. He's from Pisa originally, and he spends some time later on in life teaching there, and then moves to Padua, where he has some success teaching at the university. But really his best move comes when he figures out how to take an invention that was dreamed up by the Dutch and turn it into a useful military tool for the Venetian navy. Essentially, the Dutch had invented the telescope, so Galileo contrary to what you may have heard, did not invent the telescope, but he was able to prove that it had other uses. On land, or at sea, if you will, he realized that you could take this object, which is composed of two lenses, one which is concave and the other is convex, wrapped up in a tube. And after he had made it more precise, he realized that this could be an effective tool for spotting enemies at a great distance. And as the Venetians did as well, and they paid him a hefty sum of money to produce many more of these objects. And what really was the kicker for the Venetians was that Galileo, as a mathematician, was able not only to enhance the accuracy of the device, but was able to provide the mathematical calculations that also proved that it was no trick of the eye, that it wasn't just some kind of snake oil that he was peddling. So like I said, he does have a keen interest in astronomy and mathematics, how those one relates to the other, and naturally being, of course, a humanist scholar also, he notices Aristotle, and he knows there's tons of problems with it, and he sets out to disprove things that he has taken particular umbrage with in Aristotle's formulations. And one of those, of course, is essentially what we will come to be known as gravity later on, especially after Isaac Newton formulates his theories. But and in order to disprove Aristotle's idea that weights of objects of the same weight will necessarily fall at the same rate, he climbs to the top of the Leaning Tower of Pisa and drops essentially bowling balls or cannonballs, if you will, not bowling balls, from the top of it. And he proves, using a 1 pound weight and a 100 pound weight, that they both drop to the ground and hit the ground at the same moment. And so this is, again, another nail in the coffin of Aristotelian physics. In 1610, he publishes his very famous Messenger of the Heavens. And what this is his observations on the phases of the moon and also on the surface of the moon using his cannocchiale, his eye read, the telescope, which you see here, which is now kept in the Galileo Museum in Florence. And essentially the importance of this work can't be understated because, first of all, he proves that heavenly bodies are not perfect spheres, as Aristotle taught. So you have ridges and craters, and also the idea that the moon goes through phases. All of these things are conflicting with traditional Aristotelian teachings, and also the Church's teachings about God creating the universe in all its perfect forms. And he also postulates then later in his dialogue on the two chief systems of the world, which you will be reading again for next week, for this week, that the laws that apply to Earth also apply out in the cosmos. So they would apply on the moon just as they apply here on Earth. And this is all very, very dangerous to the Catholic Church. It's really tearing at what has for so long held together classical knowledge as well as Christian doctrine. So in 1633, unfortunately, he's dragged before the Inquisition in Rome, and he's forced to recant his theories. And he has to spend the rest of his life, a measly 9 years, confined to his house in Florence. The Medici themselves, being patrons of Galileo, had for a time done as much as they could to shield him from the Inquisition. But there's only so much that even a powerful patron like the Medici could do in this particular case, because it was such a high-profile case of heresy. So for your reading this week, you will actually be reading the dialogue on the two chief systems of the world, which does take the form of a dialogue, which is rather interesting. It's perfectly keeping in line with a lot of texts of the period who would use this kind of dialogue form to talk about anything from philosophical ideas to religious ideas to mathematics. And even though Galileo said, well, it's just a fictional situation, it's just a couple of guys, sitting around talking about things. They're fictional characters, of course. I'm not actually meaning to say that I want to refute the church's teachings. Of course, the church unfortunately doesn't buy this. But you again will be reading that for this week. So I hope that you all enjoy reading Galileo as well as Eric Cochrane. The third book for this week is very entertaining, and I will see you all on the discussion boards.